the 3I Atlas mystery. There are instances in astronomical research when a routine observation uncovers an extraordinary phenomenon, and that phenomenon compels us to question the foundations we've built upon. For over 100 years, we've monitored comets and asteroids as they traverse the solar system, each one governed by the expected forces of gravitational pull, solar pressure, and spin. Yet occasionally an object emerges that defies our predictions. See, 2024 3I Atlas represents precisely such an anomaly. When it initially registered on our detection systems, we recognized at once that it was extraordinary. Its arrival path, its exceptional speed, and its orbital characteristics definitively marked it as an interstellar interloper, the third we've documented. Following one eye, Oumuamua, and two eye, Borisov. This distinction alone rendered 3I Atlas deserving of rigorous investigation. Interstellar bodies offer us insight into substances and compositions from star systems distant from ours. They serve as cosmic couriers from alien suns. Yet what has become apparent in the period following its detection is something considerably more extraordinary. 3I Atlas isn't merely traveling through our system, it's experiencing a modest yet quantifiable non-gravitational thrust, one that's steering it toward a remarkably specific destination within our solar system. That destination is Jupiter's gravitational domain, its Hill radius. And the predicted minimum separation based on contemporary calculations is 0.357 astronomical units. That figure might appear random initially, but from a research standpoint, it's extraordinary. This separation positions 3I Atlas, essentially right at the edge of Jupiter's Hill sphere, a zone where the gas giant's gravitational pull supersedes the sun's. For natural bodies arriving from interstellar depths, such a precise targeting is uncommon. Indeed, as celestial mechanics demonstrates, this is extraordinarily improbable. This alignment, the 0.357 AU closest approach, represents our fundamental puzzle. And the deeper we examine the path, the more we discover that the chemical, physical, and orbital data point toward a unified interpretation. 3I Atlas is experiencing influences beyond simple gravitation. Some of these influences are directly observable in its outflow, mass depletion, and coma characteristics. Others must be determined through mathematical analysis in the form of delicate, continuous thrusts. Today, I want to guide you through what we've established, why the 0.357 AU separation is significant, and what this tells us about interstellar dynamics. I also want to distinguish what research can affirm today without embellishment or conjecture, because the narrative of 3I Atlas isn't simply about peculiarity. It's about what meticulous observation enables us to reveal. Understanding the Hill sphere boundary. To comprehend why the 0.357 AU encounter matters, we need to start with the Hill sphere concept. Every planet possesses a spatial region surrounding it where its gravitational force prevails over the sun's. For Earth, this radius is comparatively modest, roughly 1.5 million kilometers. For Jupiter, our solar system's largest world, the Hill sphere is enormous, reaching beyond zero. 355 astronomical units. That value, 0.355 AU, marks the threshold where Jupiter's gravitational dominance takes effect. Bodies entering this territory can experience capture, disruption, or trajectory changes through intricate dynamics. Now, consider this. 3I Atlas is calculated to pass at 0.357 AU, just 0.002 AU beyond that threshold. That gap is roughly 300,000 kilometers less than the Earth-Moon separation. This prompts two crucial questions. What are the odds that an interstellar body would pass this close to this gravitational threshold purely by coincidence? Why is the path converging on this location despite continuous non-gravitational thrust? To address the first question, we evaluate probability. Employing fundamental orbital calculations, we can determine the chance that an arbitrary interstellar path intersecting our solar system would transit within Jupiter's Hill sphere. The probability is remarkably tiny, approximately 1 in hundreds of thousands. To address the second question, we must examine the detected thrusts, because when we integrate non-gravitational influences from outgassing into path projections, this near-perfect encounter remains. This is where scientific inquiry becomes particularly compelling. It indicates that the identical physical mechanisms driving mass depletion are affecting the path in a steady manner. This isn't without precedent. Comets display non-gravitational thrusts regularly, but the accuracy of this encounter is remarkable for an interstellar visitor with no previous connection to our stellar neighborhood. This accuracy is why the 357 AU number holds significance. It's not simply a near pass, it's a near pass at the precise threshold where Jupiter's gravitational control becomes paramount. In essence, 3I Atlas is navigating through an extremely confined gravitational gateway. The forces shaping the trajectory. To comprehend the path, we examine the influences operating on 3I Atlas. During the initial observation period, July, August, and September, 3I Atlas displayed negligible non-gravitational thrust. This permitted us to calculate a minimum mass boundary, approximately 33 billion tons. This mass is considerable even by cometary standards. However, approaching perihelion in October, conditions shifted. The body began demonstrating substantial non-gravitational thrust, quantifiable at a confidence level surpassing 10 sigma. For context, a 10 sigma measurement far exceeds standard benchmarks in physics or astronomy. This confirms the thrust is genuine, not measurement noise or systematic error. Such thrusts emerge when material is expelled from a body in a directional pattern, producing reactive force. In natural comets, this happens through sublimation, ice transitioning to vapor under solar thermal input. The gas streams from the surface, generating recoil that modifies the path incrementally. For typical comets, this force is minor and chaotic, influenced by rotation and uneven venting. For 3I Atlas, it appears more sustained. The path is adjusting in a direction consistent with the outflow direction. If we presume natural sublimation, the mass depletion necessary to generate this thrust exceeds 10% of the minimum mass calculation, representing billions of tons of substance released over months. This magnitude raises questions. How much volatile content does 3I Atlas harbor? What constitutes these volatiles? And why is the mass depletion so prolonged at its solar distance? Chemical clues and volatile activity. Certain answers emerge from spectral analysis. Among the most peculiar discoveries is that 3I Atlas demonstrates vigorous activity far from the sun, well outside the zone where water ice vaporizes. This implies the existence of more volatile substances, materials that evaporate at reduced temperatures. Confirmation of carbon-containing compounds, carbon monoxide, and additional volatiles has appeared across numerous observations. In certain enhanced spectroscopic examinations, atypical chemical indicators have been documented in amateur or theoretical discussions. However, major observatories continue working toward agreement on exact molecular determination. What we've confirmed is this: the coma is luminous. The mass depletion rate is substantial. The material ejection is powerful enough to counteract solar wind pressure in certain directions. These mechanisms can produce measurable path alterations. The extensive and persistent coma at distances around 2 AU suggests volatile-powered activity that's atypical for an inert, rocky interstellar fragment. This corresponds with predictions that interstellar bodies may contain unusual ices formed under vastly different circumstances than those within our solar system. Such volatiles can vaporize readily, creating thrust-like phenomena, the outcome being non-gravitational guidance, trajectory simulations, and convergence. This returns us to the path analysis. When we incorporate the measured non-gravitational components into trajectory modeling programs, such as those employed by JPL Horizons, a distinct pattern materializes across thousands of simulated variations of the object's trajectory, accounting for uncertainties in present measurements. All projections converge within Jupiter's Hill sphere or remarkably near its boundary. This convergence is noteworthy because natural outgassing is typically stochastic, random in orientation and intensity. Yet in 3I Atlas's case, the directionality appears uniform. The effect isn't dramatic. We're discussing extraordinarily subtle thrusts over immense distances, but the accumulated impact yields a precise encounter. The resulting trajectory leads to the close approach in March 2026, when 3I Atlas will transit at 0.357 AU from Jupiter. This is why the encounter holds scientific value. It enables us to validate our models of non-gravitational thrust. It provides an opportunity for spacecraft, including NASA's Juno mission, to study the object at reduced range. It offers a natural trial in gravitational mechanics between an interstellar visitor and our system's largest planet. This moment, the March 2026 passage, constitutes the most critical observation window available to us. The physics of improbability. Before we explore that window, we should examine the physics underlying the unlikelihood. To quantify how improbable this near intersection is, we can calculate the probability of an interstellar path passing through Jupiter's Hill sphere by chance alone. Begin with basic geometry. The Hill sphere cross-sectional area equals pi times 0.355 AU squared is approximately equal to 0.396 AU squared. Now compare this against a representative shell of space through which interstellar bodies enter our solar system. For an approach sphere with radius 100 AU, the surface area equals 4 pi times 100 squared is approximately equal to 125,600 AU squared. Now determine the likelihood. P is approximately equal to 0.396, 125,000. 600 is approximately equal to 3.15 times 10 to the power of negative 6. This corresponds to roughly 1 inch, 300,000, assuming trajectories are isotropic, equally probable in all orientations. But here's what makes this particularly significant. 3I Atlas is approaching the boundary not once coincidentally, but consistently throughout every simulation. Excluding the thrust, the object wouldn't intersect near the boundary. Including the thrust, it does, and the orientation of that thrust is persistent enough to generate convergence. Put differently, the non-gravitational influences are directing 3I Atlas toward the 0.357 AU encounter. This represents the technical definition of non-gravitational steering. It doesn't suggest anything artificial, only that influences beyond gravity are determining the path. The character of those influences, mass loss, jets, rotation, remains under investigation. Scientific opportunities ahead. The approaching encounter presents multiple research possibilities. Imaging by NASA's Juno spacecraft. Juno, currently orbiting Jupiter, may be positioned to observe 3I Atlas during its nearest approach. This depends on mission coordination and relative positioning. A window spanning March 9 through the 22nd of March 2026 appears most favorable. Even at 0.357 AU, Juno may be capable of detecting coma architecture, jet configuration, rotational characteristics, surface reflectance, dust particle distribution. This would mark the first spacecraft observation of an interstellar body since Oumuamua. Ground-based spectroscopic studies. Major telescopes, including facilities in Chile, Spain, and Hawaii, will conduct high-resolution spectroscopy to verify volatile composition, track changes in mass depletion, identify rotational signatures, quantify Doppler shifts from jet activity, trajectory refinement from JPL horizons. Minor changes in the path during late 2025 and early 2026 may disclose rotational torque, three-dimensional mass loss structure, thrust variability. This will permit us to reconstruct the physical forces directing the object's course. Validation of interstellar comet models. This encounter provides us a unique opportunity to test our theories of non-gravitational thrust, outgassing physics, volatile preservation in interstellar bodies, surface characteristics of extrasolar planetary material. This is why the 0.357 AU encounter holds such importance. It's not simply a close flyby, it's a controlled experiment provided by nature. What science can tell us? Research advances by separating three categories. What is established? What remains unknown? What cannot be determined with present data? For 3I Atlas, here's what we've established. It's interstellar verified through orbital parameters. It's depleting mass rapidly. It's experiencing quantifiable non-gravitational thrust. The thrust is powerful enough to modify its path. The modified path leads to a 0.357 AU encounter with Jupiter. The probability of this occurring by chance is minimal. The event will take place in March 2026. Juno and Earth-based observatories can study it. Here's what remains uncertain: the precise volatile composition, the detailed internal architecture, the rotation period with complete certainty, whether mass depletion is constant or intermittent, the degree of dust shielding within the coma, the effects of solar-wind interaction on jet alignment, and here's what we may not determine until March 2026. The comprehensive physical morphology of the nucleus, the three-dimensional structure of the jets, the mass distribution throughout the coma, the rotational phase during nearest approach. Yet what we'll obtain is extraordinary. This marks the first instance we've been capable of forecasting months ahead a close encounter between an interstellar body and a major planet. This allows us to prepare. 3I Atlas is granting us direct access to a natural experiment involving interstellar material, mass loss physics, volatile chemistry, cometary mechanics, gravitational boundary dynamics. This represents, in every respect, the emergence of interstellar object science, a cosmic opportunity. When we study 3I Atlas, we're not simply examining a curiosity from another star. We're observing the interaction between the familiar and the foreign, between the predictable mechanics of our solar system and the unpredictable characteristics of a visitor formed far away. The 0.357 AU close approach stands as the most fascinating dynamical feature we've ever documented from an interstellar object. It represents an unusual convergence of forces, gravity, outgassing, rotation, and solar radiation, producing a trajectory that threads the boundary of Jupiter's gravitational territory. Research progresses through opportunities. Sometimes nature delivers precisely the experiment we require, at precisely the moment we can witness it. 3I Atlas represents such an opportunity. The coming 16 months will establish how much we discover. And the more we observe, the more the universe demonstrates its capacity to astonish us. Whether the story of 3I Atlas ultimately becomes one of natural physics or previously undiscovered chemistry, it will enhance our comprehension of interstellar space. The close approach in 2026 won't mark the conclusion of the mystery, but it will mark a beginning, because each interstellar visitor imparts something new. With 3I Atlas, the lesson appears to be this: the universe doesn't merely send us objects, it sends us questions. And it's our responsibility to observe carefully, analyze rigorously, and let the evidence guide the way.